For any assignment-related queries, call us at +1 678 648 4277. You can mail us at support@solidworksassignment.com or reach us at https://www.solidworksassignmenthelp.com. Solid Mechanics Assignment Help. Mechanics and Materials Problem 1. The stiffness of a linear elastic structure subjected to a force of magnitude F, which results in a displacement of the load point in the direction of the force of magnitude delta, is given by Figure 1. Cantilever beam. A. Axial loading. B. Lateral loading. SolidWorksAssignmentHelp.com. Consider the case when the structure is, say, a tip-loaded cantilever beam, as shown in the figure. Depending on the orientation of the applied load with respect to the beam axis, two different stiffness values result. When loading is parallel to the beam axis, the axial stiffness of the structure can be defined as where it is understood that delta x is the axial displacement of the tip under load Fx. When the applied load is perpendicular to the axis of the cantilever, a bending stiffness can be defined as where delta y is the lateral displacement of the tip under transverse load Fy. The beam is of length L and has cross-sectional area A and area moment of inertia I. Under the usual assumptions of slender beam bending theory, L is much greater than linear dimensions of the beam cross-section, including both 1 is identical to square root A and 2 is identical to I/A, that is, L1 and L2. Show that the ratio of a slender cantilever's bending stiffness to its axial stiffness is extremely small, and give a precise expression for this ratio in the case of a solid circular cross-section of diameter dl. SolidWorksAssignmentHelp.com. Problem 2. When a cantilever beam is subjected to a temperature change that varies linearly through its thickness, but does not vary along the length of the beam deflects laterally with a constant curvature, kappa, thermal, with resulting lateral displacement field. Similarly, the mid-surface axial displacement field is given by where 0, a thermal, is a dimensionless constant. Here it is understood that the base of the cantilever is at x equals 0, while its tip is at x equals L. Let the beam cross-section be rectangular, of width b, in direction, and thickness h, in I direction, and let the temperature change very linearly with the I-coordinate according to. So that the temperature change at mid-thickness, y equals 0, is delta T0, at the bottom of the beam, y equals minus h/2, it is delta T0 plus delta T, and at the top of the beam, y equals plus h/2, it is delta T0 minus delta T. Aside, according to Fourier's law of heat conduction, linearly varying temperature fields such as this are associated with a steady flow of heat from the higher temperature region to the lower one. SolidWorksAssignmentHelp.com. Show that the curvature of the thermally loaded cantilever is given by independent of the value of delta T0, and that the axial mid-surface strain is given by independent of the value of delta T. Show that there is zero axial stress everywhere in the thermally loaded cantilever, just decrebitation. If, instead, the thermally loaded structure is also subjected to a boundary condition at its tip that requires zero lateral displacement, V, x equals L, equals 0, then non-zero reaction forces and axial stress will be generated. Using thermo-elastic superposition, evaluate the magnitude of the tip reaction force, tip, required to bring the total tip deflection in the thermally loaded and tip-restrained cantilever back to 0, i.e. SolidWorksAssignmentHelp.com. Figure 2. Tip-restrained cantilever beam subjected to a temperature change varying linearly with through thickness coordinate. Where V delta T, x equals L, is the tip displacement of the free thermally loaded cantilever above, and equals VRL, is the tip displacement of the cantilever in response to tip, x lateral load of tip applied at x equals L. Identify the location of maximum tensile stress in the thermally loaded cantilever having restrained tip displacement total, x equals L equals 0, and symbolically evaluate the tensile axial stress at that location. Suppose that the beam with tip restraint is made of steel, with E equals 210 GPa, alpha equals 12 times 10⁻⁶/K, and has dimensions L equals 100 mm, B equals 15 mm, and H equals 3 mm. What is the largest bottom/top difference in temperature change, parametrized by delta T max, so that the steel does not reach a yield strength of sigma y equals 350 MPa? Solidworks assignment help.com. Problem 3. The mass density of a crystal can be calculated from a knowledge of the unit cell of the crystal, the atoms within the cell, and their atomic weights. As an example, consider iron, Fe, which has a body-centered cubic, BCC, crystal structure. A unit cell contains 9 iron atoms, with 8 of them located on the corners of a cube of edge length R0 equals 0.2866 nm, plus 1 additional iron atom at the center of the cube. By translations of this unit cell in the 3 principal cube directions, an arbitrarily large crystal can be generated. Evidently, each corner atom of the cell participates in 8 is equal to 23, different unit cells of this sort, thus only 1/8 of the mass of the corner atoms should be assigned to this unit cell. Reflection will show that the net number of iron atoms in the cell is 2 is equal to 1 plus 8 times 1/8, where 1 denotes the central atom. Mass density is defined as: when applied to a unit atomic cell, we can generalize this result as the atomic mass of iron, check out a periodic table, is 55.847 grams per mole, and the Avogadro number is Na is equal to 6.02 times 1023 atoms/mole, so the atomic mass of iron is 55.847/6.02 times 10⁻23 g/atom. Show that the Calculayan outlined predicts a lattice-based estimate of the density of iron as Solidworks assignment help.com, which is slightly larger than the measured density of iron, 7.87 megagrams per cubic meter. The slight discrepancy is due to the presence of defects in the actual crystal. Defects were ignored in the model. Sodium chloride, salt, is an ionic crystal for which a simple unit cell can be constructed, consisting of alternating sodium, Na, and chlorine, Cl, atoms spaced a distance are 0 apart along lines of a cubic grid. An 8-atom section of such a cell is shown. Assuming the density of salt is NaCl equals 2.17 megagrams per cubic meter, estimate the lattice spacing, R0. Figure 3, Unit Atomic Cell, BCC, 4 Fe. Dashed orange lines connect central atom to corner atoms. Not all shown, for clarity. Solidworks assignment help.com. Figure 4, Unit Atomic Cell for Nazi. Problem 4. In our simple model of atomic spacing, R0, and atomic bond stiffness, S0, we argued that the elastic modulus, E, should scale as, and concluded that the orders of magnitude differences observed in E among solids, along with only a factor of 2 or so variation in R0, pointed clearly to the dominant role of bond stiffness, S0, in scaling elastic modulus. We further grouped dominant classes of primary bonds as covalent, metallic, ionic, and weak polarized bonding, van der Waals, hydrogen bonding. Solidworks assignment help.com.